So we're going to look at stationary points, critical points. A stationary point is where the derivative is equal to 0. In other words, we imagine the slope of our tangent line is equal to 0. That would mean that it's horizontal. It's flat, and that's going to happen, we've already seen, when we have local maximum points and local minimum points. So here's our definition of a stationary point. And here is our definition of a critical number or a critical point. We also saw in one of our examples that we had some non-permissible values. So we call a critical point either a stationary point where the derivative is equal to 0 or where our function is undefined, because things can change at those points as well. So we're going to look at where a graph has asymptotes. So there are three types of stationary points. The ones that we've seen so far have been local minimums and local maximums. Sometimes they're a relative maximum or a relative minimum, meaning that they're the biggest or the smallest value in the entire function. Like in a parabola, the parabola's minimum would be a relative minimum because it doesn't get any lower than that. But sometimes in a cubic function, you would have a local maximum because the function continues up forever, but you still have a small maximum within that. So we've got our relative maximums. You can imagine that in a parabola like this. You have local maximums and local minimums. If I had a cubic graph like this, that would be a local minimum. And a stationary point of inflection, that happens in an x cubed graph. An x cubed graph looks like this. This point right there, the tangent is 0, even though it's not a maximum or a minimum. So what do we notice about a function? If a function has a maximum, if you pick something before that, I'll color code this. Let's make this section before the maximum green, the section after the maximum to the minimum red, and the section after that minimum green again. Notice in that green section that if I pick any point on that green section and drew a tangent at that point, that tangent would always be positive. But if I picked any point after the maximum and drew a tangent line there, then we would have a negative. And of course, after the minimum, again, we have a positive. And we did this before we drew our number line. We found out on our number line that here and here were where our tangent was equal to 0. Then we checked values before, and if you found this section to be positive, you knew your function was increasing. This section to be negative, you knew your function was decreasing. And finally, positive again meant that it was increasing. And if we draw this diagram and draw the arrows the way that we've drawn them, it's really easy to see that this one's going to be a local max, and this one's going to be a local min, because our function is going up to that value and then down, and after it's going down and then back up again. And here is what happens in our horizontal inflection point. We've got our stationary point of inflection. Again, we would have found out that this is where our tangent is equal to 0. But when we check something before and something after, no matter which point I pick and think about my tangent lines, they're both going to be positive. So my function is increasing and increasing again. So the way that that works is our graph is going to be increasing, it's going to flatten out, and then start to increase again. And again, this happens in graphs like y equals x cubed. So this little diagram that we've been drawing here, where we put our critical numbers on there and then check where it's increasing and decreasing, it has a name. We're going to call it the first derivative test. So what it says if our derivative changes from positive to negative at our critical point, it's going to have a local maximum. So the way that we're going to see that is we make our number line and we put our critical point on our number line. And if at C our derivative changes from positive, which means it was going up, to negative, which means it would be going down, it's easy to see that C has to be a local maximum. Similarly, if we had that point C and we noticed before it was negative and after it was positive, it's easy to see that on our original graph, that would have to be a local minimum. So, anytime we change from an increasing function to a decreasing function, in other words, your function's going up and then it's going down, that has to be a local maximum. When we look at a derivative, our derivatives change from being positive to being negative. And anytime you change from a decreasing to an increasing, again, you're decreasing and then you go to an increasing, that would have to be a local minimum. And again, the derivative now is changing from being negative to being positive. And of course, at point C, that's where your derivative is equal to 0. So here's our first examples. Basically the same thing that we were doing yesterday, except now we have a name for what we were doing. We're going to use the first derivative test to classify these stationary points in the following functions. So the first thing we're going to do is we're going to take the derivative. And we're just going to add some of the terminology we learned that's different from what we did before. So we've taken the derivative. The next thing we're going to find is our critical points. Well, how do we find our critical points? We're going to look for non-permissible values, and we're going to look for where the derivative is equal to 0. This derivative has, or our original function, has no non-permissible values. So as far as our critical points are concerned, we're only going to be looking for stationary points, and we find our stationary points by making our derivative equal to 0 and solving. And now we can call the number line that we use to put our critical points on, that's our first derivative test. So we have our number line. We put our critical value, 5 over 2, on there. And we're going to check values before 5 over 2 and after 5 over 2 to see what's happening. If I plug in a number before 5 over 2, like 0, it's positive, meaning our function had to have been increasing before that. And if we plug in a value after 5 over 2, say 5, we get a negative so that we know that our function is decreasing. So now we can answer the question. We can classify our stationary points. So our stationary points here, well, we know the x coordinate is 5 over 2. If we want to find out what the y coordinate is, this is a point on our graph. So we have to go to our original function and plug in 5 over 2. Someone have their calculator handy? That was an attempt at quick mental math, which most likely will be off. Oh, maybe right. So this is our point, and it is, well, in this case, since we know it's a parabola, local maximum. It's a local maximum. We could also call it an absolute maximum. So now we have our stuff here. We can do the derivative to find our critical points. We now know that our sign diagram that we've done here, we can call it the first derivative test, and we can solve from there. So try this one. Put up the answer in a second. All right, if you want to check how you did, took your derivative, found your critical point to be at 2. Here we have our first derivative test. And when you plug in values into your derivative, this would have been negative. This would have been positive. So now we know that that is a local minimum. We can plug into our original function to find the y value of -3. And so we can classify our stationary point to -3 as a local minimum. Again, take the derivative, you can factor it. First derivative test, goes from positive to negative to positive. Plug in those values to find out what they are. So -1,5 is a local maximum, and 3, -27 is a local minimum. And finally, this last one has some non-permissible values which you have to include in there. So now in the first derivative test, if you just looked at those points, right, it would be decreasing before 0 and increasing after, but we also need to include our non-permissible values on here. So we need to look at -1 and +1 and check those values as well. Because it is possible that with those additional critical values, that it could have been increasing before this, then decreasing, then increasing. And if you had chosen your critical point in the wrong, or chosen your test value in the wrong section, you could get a misleading value for our critical point at 0 and not find out that it's a minimum. Fortunately, in this case, if you had plugged in a value less than -1, it was still negative before that and decreasing in both of those parts. And if you had tried a value larger than 1, it was still positive after that and increasing here. So in our first derivative test, with all of our critical values, we would still find out that our point at 0, 4 would be a local minimum.